often hear people say, correlation does not imply causation, as a way of cautioning you from making unwarranted conclusions from scientific data. But science does at least sometimes give us knowledge of causal relationships in the world. For instance, we know that smoking causes cancer, that increased levels of greenhouse gases in the atmosphere cause the global temperature to rise, and that interrupting the electrical circuit connecting my switch and my light bulb causes the light to go out. But as we learned when thinking about experimental design, all an experiment or observational study provides us with is a data set of correlations between the values of the independent variable and the dependent variable. So if experiments and observational studies give us correlations between variables, and correlation does not imply causation, how can we learn about causes through science? As it turns out, this is a complicated question. So first, let's think about why it's true that correlation does not imply causation. What that means is just because you've identified a correlation between two variables, that doesn't mean that you can conclude that the value of the independent variable causes the value of the dependent variable. In fact, the correlation may be totally coincidental, or it may be that the values of both variables are caused by some common causal factor that you haven't thought about. Or it may be that the causal relationship actually goes in the other direction. Or it may be that the independent variable is only part of the story about the causes of the dependent variable. So there are a lot of ways for the inference from a correlation to a causal relationship to fail. Here's one famous example. There's a very strong correlation between the number of ice cream cones sold and the number of shark attacks. Can we conclude from this that the ice cream cone sales cause the shark attacks? No, of course we can't. Ice cream cone sales have nothing to do whatsoever, causally speaking, with shark attacks. What we're seeing here is two variables that have a common cause. Both ice cream sales and shark attacks are caused by warmer weather. When the weather's warmer, more people buy ice cream cones, and it's also true that when the weather's warmer, more people go swimming at the beach. More people swimming in the ocean is what leads to a higher number of shark attacks. But how can we use the tools of science to establish causal relationships and not merely correlations? One way to understand how this is possible is to think of causal factors as being the element of the setup that would have made a difference to the outcome. So if you were to run the experiment again and intervene on the independent variable, and that makes a difference to the value of the dependent variable, then you've identified a causal relationship. So back to the shark attacks. If you were to close all the ice cream shops so that ice cream sales dropped to 0, would that make a difference for the number of shark attacks? Nope. The number of shark attacks would still go up in warm weather and down in cold weather, even if we were all deprived of ice cream. This is sometimes called a difference-making view of causes. When the intervention on one variable makes a difference to the value of the other variable, then there's a causal connection. Thinking in these terms can be useful in designing experiments to test whether a known correlation indicates a causal relationship. If your data show a correlation between the value of the independent variable and the dependent variable, then a follow-up experiment where the value of the independent variable is changed will give you more information about whether it's truly the cause of the value of the dependent variable. Another tool for identifying causation in some circumstances is seeking to find whether the suspected cause has a physical influence on the suspected effect. Think of the example of a light switch turning on a light. The action of my flipping the switch closes a circuit that is made up of wires in the wall and that allows electricity to flow from the main power source through the wire to the bulb. The flowing electricity is what is responsible for the light in the bulb. There's a continuous physical process that connects my flipping of the switch with the light bulb illuminating. It involves the switch moving, electrons flowing through the wires in the wall, and the electricity producing the light in the bulb. Discovering that physical influence shows us that flipping the light switch caused the light to turn on. There's no such physical process that connects the higher rate of ice cream cone purchases with shark attacks. But the story about warmer weather does have a physical process explanation. Everyone who swims in the ocean has a small but non-zero chance of being bitten by a shark. Again, it's a small chance. When the weather gets warm, more people are more likely to decide to go to the beach, meaning that there will be more people in the water. The increased number of people in the water means that even though the probability of getting bitten stays the same for everyone, more bites will occur since more people are exposed to the risk. And for each bite, there will be a physical process story about that person's choice to go to the beach and the shark's particular position, which will explain the connection between the weather and the shark bite. The view of causation associated with this strategy is sometimes called a physical process view of causation. There must be a continuous physical influence of one variable on another in order for there to be a causal connection. These two views of causation are not incompatible with each other, but they serve different purposes. A difference-making approach is more useful when physical connections between variables are difficult or impossible to discover, and the physical process approach is more useful when it's important to know how one variable causally influences another.